Welcome to EDU World Space.
So in this question, we are given a soft material, right, that is placed within the confines of a rigid cylinder, right? So we have a cylinder, and inside this cylinder, we have a soft material which rests on a rigid support. Now, what we're going to do, as per the question states, that assume that the strain in the x direction is zero and the strain in the y direction is also equal to zero. And after assuming this, we need to determine the factor by which the stiffness of the material or the apparent modulus of the elasticity will be increased, right? When a load is applied and if the epsilon is equal to zero point 0.3, right? So let's start with the solution. Now the solution is very simple. It's a little bit lengthy, but it's very easy, right? So now, as you can see that there is a little ambiguous, this question is a little ambiguous, right, at the first sight. And it's asking for the factor by which the modulus of the elasticity is increased, right? The factor by which the modulus of elasticity is increased, right? Now, this means that we want to compare the normal, let's say, modulus of elasticity with the of this material with the one it has while it confines in the rigid cylinder, right? So let's say that this is the normal one and E nu is the one that with which we want to compare it, right? So let us start considering what would happen to the material if it weren't in the confines of the cylinder. So in this case, there is only one load that is applied uh, to the cylinder, right? So the stresses would be in the x direction and in the y direction that would be equal to zero, right? And the stress in the z direction, it would be equal to the power divided by the area, right? Now in this case, the strain in the z direction would be from the Hooke's law, right? It would be stress in the z direction divided by the elasticity. And what we are going to do is that we are going to analyze the case given the problem because of the symmetry, right? So because of the symmetry, we would have the stress in the y direction equal to the stress in the x direction, right? It's because of the symmetry that it is not a valid argument in our case. Then we'll simply take the Hooke's first and second equation, and since both shear stresses are zero, so we'll get that the stress in the x direction is equal to the epsilon and parentheses the stress in the y direction plus the stress in the z direction, right? And the stress in the y direction is equal to the epsilon parentheses stress in the x direction plus stress in the z direction, right? Now what we're going to do is that we are going to subtract this equation from this equation, right? So it means that we would have stress in the x direction negative the stress in the y direction, right? And that is equal to the epsilon stress in the y direction plus stress in the z direction negative epsilon stress in the x direction plus stress in the z direction, right? Now what we're going to do is simply that we are going to rearrange it, right? So we have stress in the x direction 1 plus epsilon that is equal to stress in the y direction 1 plus epsilon, right? We have just simplified it and did some basic algebraic manipulation with this equation at this very step, right? And we got this equation after rearranging it, right? And since this cancel out, so we have the stress in the x direction equal to the stress in the y direction, right? Now, this above is the actual proof. So, moving forward and taking the Hooke's first and second, Hooke's laws first and second equation, right? So, and before doing that, remember that the strain in the x direction is equal to strain in the y direction, that is equal to 0, right? So, we have 1 divided by the new elasticity, modulus of elasticity, right? So we have stress in the x negative the epsilon, stress in the y plus the stress in the z, right? That is equal to 0. So the stress in the x negative epsilon stress in the x epsilon stress in the z is equal to 0, right? And this is equal to 1 negative epsilon z, right? So finally, we'll use this in the Hooke's law equation, right, for the z-axis, and we'll get that the strain in the z direction is equal to 1 divided by the new epsilon, right, square bracket, stress in the z direction, negative the epsilon, and in the closed parenthesis will be the stresses of the other directions, right, that is x and y, and this is equal to 1 divided by the new modulus of elasticity. Over here we have z negative 2 epsilon x, right? Because this is they are same, right? So if I substitute this over here, so it wouldn't make any difference, right? So now I'm going to rearrange it. So I have z negative 2 epsilon square divided by 1 negative epsilon z, right? And again, I'm going to simplify a little bit more. So I have the new modulus of elasticity, and over here I have 1 negative v, 1 negative v. Some basic algebraic manipulation, nothing very technical is going on over here, right? This is basic algebraic manipulation, and in the end we'll get this expression, right? So I have divided by 1 negative v, right? So now all we have to do is to find the ratio, right? We need to find out the ratio of E and like the normal modulus of elasticity to the new modulus of elasticity, right? Which we can do by dividing the left and right side of the two equations we found as like this, right? So I have the strain in the z direction to the strain in the z direction, right? The stress in the z direction divided by the new modulus of elasticity. Over here I have divided by this, right? And I'm going to multiply it with the normal modulus of elasticity divided by the stress in the z direction, right? Now, as you can see, this will cancel out, right? So, and so what? This one, so we'll be left with 1 is equal to E divided by new modulus of elasticity, right? And this would be divided by 1 minus, right? So I'm going to rearrange it, right? So I have this on the left hand side, and on the right hand side we have, I'm plugging the values over here as well, right? So I'm skipping a step. So we have divided by 1 minus 0.3 square, right? And this is equal to 3.61, and that is approximately equal to 1.35, right? So this concludes our answer.